Hello, everybody. This is Mr. Pisoni. This is the video for chapter 9.1. So chapter 9 is all about trigonometric ratios and functions. And 9.1 was specifically about right triangle trigonometry. So today I'm going to work some of the problems from the book on 9.1, just to give people a little bit more insight on how to do these problems. We already talked about all of this in the lecture in class. So let's actually go to some of the problems. Let's see, where are they at? Okay, so the first type of problem for goal 1.a was evaluating trigonometric functions, where we were given a right triangle and 2 out of the 3 sides of that triangle. And then we had to find the 6 trig functions for theta. So we're going to have to use some Pythagorean theorem as well as what we know about trig functions. So let's go ahead and get started on this. So the first triangle I have has side lengths of 9 and 12. 9 and 12. And then a theta up in this upper left corner here. So remember, all the trig functions are done from the perspective of theta. So if theta is over here, the opposite side is going to be the side across the triangle from theta. So we know that the opposite is 12, and then the adjacent will be 9, side that we have next to us. And of course, now this side here is going to be the hypotenuse, and I have to calculate that using the Pythagorean theorem. So the hypotenuse is going to be equal to, well, hypotenuse squared, rather, is going to be equal to 9. What is going on with my pen here? It's going to be equal to 9 squared plus 12 squared. So if we work this out, we end up getting 81 plus 144. Hypotenuse squared is 81 plus 144. 81 plus 144 is going to be 225. And the square root on both sides, that means that the hypotenuse is equal to 15. This is actually a special triangle. It's a 3, 4, 5 triangle where the sides have been multiplied by 3. So instead of 3, 4, 5, it's 9, 12, 15. So our hypotenuse is 15. And then at this point, all we have to do, I change my font size there. All we have to do is fill in what we know for our 6 functions. So sine of theta would be equal to opposite over hypotenuse. And opposite in this case is 12, and hypotenuse is 15. 12 over 15 reduces to, not 3, to 4 over 5. And actually, I'm going to change my size back there. And we can continue this with the other functions as well. Cosine of theta will be adjacent over hypotenuse, which will be 9 over 15, which will equal 3/5 when we reduce it down. And we can continue doing this for all of them. Tangent would be opposite over adjacent. Opposite is 12, adjacent is 9, which is going to reduce to 4/3. Once I found these 3, remember these are my primary functions, sine, cosine, and tangent. That means I can find the secondary functions by just taking their reciprocals. So cosecant of theta is going to be 5 over 4. Secant of theta is going to be 5 over 3, and cotangent of theta is going to be 3 over 4. So as you can see, this comes together pretty quickly. We'll do 2 more of them just to kind of work it out. So in this second one, we've got 2 sides that we know, 7 for the hypotenuse and 5 for one of the 2 sides. In this case, 5 is opposite because it's across the triangle from theta. If I want to figure out the adjacent side, it's going to be, well, if you think about the Pythagorean theorem, it's going to be opposite squared plus adjacent squared equals hypotenuse squared, or a squared plus b squared equals c squared. So that's going to be 5 squared plus something squared equals 7 squared. So 25 plus adjacent squared equals 49. You do some quick math and you get adjacent squared equals 24. I'm going to move that, move all of this actually. Going too much into the next area. So we have 25 plus adjacent squared equals 49, which means adjacent squared equals 24, which means adjacent is just going to be the square root of 24. We can leave it like that as the square root of 24. You can get a little bit fancy if you want by solving the square root of 24 for a more specific answer. You can factor or you can pull a 2 out of that root, because the square root of 24 is technically the square root of 4 times the square root of 6, which is the same as saying 2 times the square root of 6. You can do that if you want. I would just leave it square root of 24. So I've got my 3 sides, 7, 5, 7, and square root of 24. So my my opposite side is equal to 5. My adjacent side is equal to the square root of 24, and my hypotenuse is equal to 7. And then from there, I can fill out my trig functions. Sine is just going to be opposite over adjacent. That's 5 over the square root of 24. Well, this is technically a valid number or a valid fraction. We like to rationalize the denominator. So I'm going to multiply both the numerator and the denominator by the square root of 24. And what I get there is 5 over the square root of 24 over 24. Cosine, going to work very similarly. Oops, and I just did this wrong. I apologize. Let me go back and fix this. Going too fast for my own good. Sine is opposite, which is 5 over hypotenuse, 7. Sine is 5/7. Cosine is the square root of 24 over 7, which I would then actually do nothing with. That's a perfectly fine fraction. And then tangent is opposite, which is 5 over adjacent, which is the square root of 24, which is where I have to rationalize the denominator. And I get 5 times the square root of 24 over 24. I've got my 3 primary functions figured out. The secondaries go very fast. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, but I have to rationalize it. And I get 7 times the square root of 24 over 24. And then tangent is the reciprocal of, or I'm sorry, cotangent is the reciprocal of tangent. And in this case, that would just be the square root of 24 over 5. I took the reciprocal of this value on the left, not this value here on the right. Even though they are equal, if I take the reciprocal of that second one, I'm going to end up with the square root of 24 in the denominator, and then I'll have to re-rationalize again or simplify it. So just stick with the first one that you had, because that reciprocal will take the square root and put it in the numerator. All right, that's 2. Let's do the third one really quick. Again, I've got side lengths of 10 and 18. So I'm going to have 10 squared plus, let's call it b squared this time. I'll follow Pythagorean a little bit. And I get 100 plus b squared equals 324. That means that b squared is going to equal 224, which means that b is equal to the square root of 224. So I can very quickly plug my values in now. I know that b was my opposite, and 10 is my adjacent, and 18 is my hypotenuse. So again, sine is going to be sine of theta. I've been lazy about writing the theta, but sine of theta is going to equal opposite, which is square root of 224 over hypotenuse, which is 18. Cosine is going to be adjacent over hypotenuse. 10 over 18, that reduces down to 5/9. And then tangent of theta is going to be opposite, which is, again, 224, the square root of that, over adjacent, which is 10. Well, now that I've got all three of those, the secondaries come fast. Cosecant of theta will be 18 over the square root of 224. We're going to have to rationalize this. So I multiply by the square root of 224 in both the numerator and the denominator. And I get 18 square root of 224 all over 224. 224 and 18 are both divisible by 2. So I can divide by 2. I get 9 times square root of 224 over 112. And I can't reduce those down any further. Secant is quick. Secant of theta is 9/5. And cotangent is also pretty quick. I get 10 over the square root of 224. I'll have to rationalize that. And I get 10 times the square root of 224 all over 224. And again, I can break this down a little bit, divide both by 2. I get 5 times square root of 224 all over 112 for cotangent. All right, so that's finding a missing side and then filling out the 6 trig functions. Sometimes we get a situation where it's described to us. I don't know if I'll do all 3 of these, but in these cases, if they're described to us, like in the first case, we've got tangent is equal to 7/6. Well, we know that tangent is also equal to opposite over adjacent, which means that opposite is equal to 7, adjacent is equal to 6. And if I wanted to find the hypotenuse, I would just do 7 squared plus 6 squared equals my hypotenuse squared. That's going to be 49 plus 36, which will be hypotenuse squared. And that's going to be, 70/85 is equal to my hypotenuse squared, which means that my hypotenuse is actually the square root of 85. Once I've got that, I found the square root of 85 is my hypotenuse, I can then quickly fill out the other 5 functions. I know tangent already, so sine is just going to be 7 over the square root of 85. I can rationalize that. If you don't see the pattern yet, when I want to rationalize something, I just take the numerator times the denominator of the original one, and then I get rid of the square root of the denominator, where I square the denominator. That makes more sense. Cosine is going to be the same idea. It's going to be 6 over the square root of 85. Again, that's going to just be 6 times the square root of 85 over 85. Tangent we already have. It's 7/6. So we go right on to the other 3 functions. Cosecant is square root of 85 over 7. Secant is the square root of 85 over 6. And then cotangent is going to be the reciprocal of tangent, which is going to be just 6/7. So it goes real fast. Some of these are a little bit backwards, secant and cotangent. I'll just get people started on these. You just kind of draw around this. So for secant is the same as hypotenuse over adjacent, which means that in the second case or the second problem, hypotenuse is 14, the adjacent is 9. And to find the opposite, all I would have to do is take 9 squared plus adjacent plus opposite squared. That will equal 14 squared. It's going to be 81 plus opposite squared plus, or not plus, 81 plus opposite squared equals 14 squared, which is 196. If I subtract 81 from 196, I get that the opposite squared is going to be equal to 115. So the opposite is equal to the square root of 115. From there, I can fill out everything. Just remember, we started with secant, so we've already got one of the secondaries, so we have to find all three primaries and the other two secondary trig functions. And then cotangent is the same idea. If cotangent is 16 over 11, well, 16 in this case would be adjacent, and 11 would be opposite. So we already have two of those values. The third one would be the hypotenuse, which would just be 11 squared plus 16 squared, which would equal hypotenuse squared. That's 121 plus 256 equals the hypotenuse squared. That's going to give me 377. That's kind of interesting. 377 is also a Fibonacci sequence value, so that's kind of interesting that 11 squared and 16 squared add up to 377. I'm sure there's some kind of weird significance there that I am not going to look into in this video. But again, once we have these values, we know that the square root of 377 is equal to the hypotenuse. And from there, all you have to do is fill in the functions using adjacent, opposite, and hypotenuse. Next up, we did some right triangle trig with special rights 30, 60, 90, and 45, 45, 90. We had to find the side lengths of x. This is very much a geometry review. So just remember, with every 30, 60, 90 triangle, the long side is always twice the length of the short side, and the medium side is the length times the square root of 3. So on this first one, the long side is equal to 12. The short side will be equal to half that. Since x is my short side, the short side is equal to 6, and that's my x. If I wanted to find the medium length side, all I would do is take my x value, which in this case is 6, and multiply it by the square root of 3. On the second example here, it's a 45, 45, 90 triangle. So in that case, remember, with a 45, 45, 90, we have two sides that are the same, and the last side is multiplied by the square root of 2. So in this case, I've got long and then the two short sides, not to be confused with too short the wrapper. So the two short sides are both equal, so x is just equal to 8. And the long side, if I wanted to figure it out, would just be 8 times the square root of 2. Very, very fast to calculate. After that, we moved on to finding the length of an unknown side and then solving the entire triangle. Solving the entire triangle meant finding 6 values, all 3 angles and all 3 sides. You need to have at least 2 of the angles and 3 of the sides to make this happen to start. Or I'm sorry, not 3 of the sides, 2 of the angles and 1 of the sides to make this work. So in this case, we've got this triangle, this diagram ABC. And I'll do the top one to the right and the bottom one to the bottom. The top one I'll do to the right, and the bottom one I will do below. So on the top one, we've got this situation. This is A, B, C, and then the far sides are, or the opposite sides from each angle or each vertex are the lowercase values for the side lengths. Well, we know that B has a angle measure of 36 degrees. We know that C, it's a right triangle, so C is 90 degrees. And we can figure out A very easily because the last angle is the angle that's going to be needed to add up to 180 degrees. So angle A is going to have to be 54 degrees. So I've already got 3 angle measures, and then I know that side length A is 23. So all I really need to do is figure out side length B and side length C. So I pick one of my two angles, doesn't matter which one. I'm going to pick 36. So my theta in this case is going to be 36 degrees. And then from there, I need to use my three primary functions. Maybe I should use yellow here. Theta equals 36 degrees. So if I use my primary functions, if this is theta, opposite is going to be b, and adjacent is going to be 23 units. Well, opposite, I don't know what opposite is yet, but what I can do is I can say that the sine, or not sine, let's use tangent, tangent of 36 degrees, my theta, is going to be equal to opposite over adjacent. Well, luckily, I already know what my adjacent is. My adjacent is 23. It's opposite over 23. So if I do some quick algebra, I'm just going to get rid of this 23 on the right by multiplying both sides by 23. I get 23 times the tangent of 36 degrees is going to be equal to my opposite. Okay, so from there, I just got to use a calculator. So I've got my calculator here. The one in Windows is nice. It's got all this stuff built into it. I'm going to take 36 degrees. I'm going to get the tangent of that, which is this nasty fraction, and then I'm going to multiply it by 23. Oops. And I get 16.7104. I'll round it to 3 decimal places, so it's going to be really 16.710 or 16.71. So 16.71 is roughly equal to my opposite. So now I've got the value for B. At this point, I can do the same thing again, using that theta of 36. Since I already had adjacent, let's go ahead and solve for hypotenuse using cosine. So I can just do cosine of 36 degrees is going to be equal to adjacent over hypotenuse, or in other words, 23 over the hypotenuse. Okay. There's a little trick you can use with a fraction. Let's move this over. Cosine of 36 degrees is equal to 23 over the hypotenuse. I'm trying to solve for the hypotenuse. Well, what you can do, I could obviously multiply both sides of the equation by the hypotenuse, but I need to get the hypotenuse by itself, so then I'd have to divide by cosine of 36. So instead, I'm just going to swap these two locations, because that's effectively what's going to happen. So what I end up with is the hypotenuse is equal to 23 divided by whatever cosine of 36 degrees is. So again, I can just quickly calculate that. 36 degrees, cosine is 0.809. So hypotenuse, oh my goodness. Hypotenuse is going to be roughly equal to 23 divided by 0.809. So I can do that calculation really quickly. And again, this is rounded a little bit, so it's going to change things, but it should be fine. Roughly 28.43. All right. So now we've got our side length C. And now we've solved the triangle completely because we know everything else. We went and found angle, what was that? Angle A? Come on. Yeah, we found angle A, which was 54 degrees. And then we solved for B and we solved for C. And just as a side note, we could use the Pythagorean theorem if we wanted to, once we had 2 out of the 3 sides. Since A is 23, I could have taken 23 squared plus 16.71 squared. That would have given me c squared. Again, I can test that real quick just to see how close it is. We did do some rounding, so it might not be exactly. So 23 squared is 529 plus 16.71 times 16.71. And that's going to give me 808.22. If I did the square root of that number, that should give me something like 28.43. I'm a little bit off. I'm 1/1000th off. Anything I give you on the homework has a little bit of wiggle room to account for people rounding at different places. Ideally, you don't want to round until the end, but sometimes if you're writing down notes, it's kind of hard to keep these long decimals in the calculator if you are using multiple things that have long decimals. So, as long as you don't round to too few digits early on, it should be pretty close. All right, so that was the first one. We found B and C quite readily. I'll do the second one. I'm going to zoom way in and make it fit here. Okay, so again, we've got a triangle. Let's use red this time. And again, it's, A, B, and C, and then lowercase a, lowercase b, and lowercase c. We know that angle A is 55 degrees on the second one. And we know that angle C is 90 because it's a right triangle. Which means if we just do a little bit of simple arithmetic, we can find angle B, which in this case would be 35 degrees. 55 plus 35 will give me 90. So angle B is measure of angle B. Let me try that again. The measure of angle B is going to be equal to 35 degrees. And then we also know, as that was given to us, that A is 17. So I need to find B and C. I can pick either one of my angles to be my theta. I'll pick 35. Doesn't really matter. I could pick 55. So theta in this case is 35 degrees. And then I just got to use two trig functions. First one is going to have to use, well, they're both going to have to use adjacent for starters. So let's do tangent. Tangent's nice because I can take tangent of 35 degrees. That's going to equal opposite over adjacent. In this case, my opposite is B. My adjacent is 17. So if I want to solve for B, it's just going to be 17 times the tangent of 35 degrees. And again, I get a calculator for that point. 35, take the tangent, and multiply the whole thing by 17. I'll get 11.904 if I round it. So B is equal to 11.904. And then if I want to find C, I could either do that fraction swap thing again, or I could change my angle that I'm doing things from, or I could change my function rather. What would be better here? Change my function, sorry, not change my angle. If I change my function to one of the secondary functions, then I've got a situation where I can have hypotenuse up in the numerator, and I can either put an opposite or adjacent in the denominator, hypotenuse in the numerator, something else in the denominator. So in this case, let's say if I want to do, let's do cosecant. If I want to do cosecant of 35 degrees, that's going to be equal to my hypotenuse, which is C, I don't know, over my opposite, which in this case is 11.904. To solve for C, it's going to be 11.904 times cosecant of 35 degrees. And again, it's calculator time. Real easy. 35, take the cosecant, I get some number, and I multiply that by 11.904. And I get, come on, I get 20.734 because I'm going to round that 3 up. So it's 20.734. So C is equal to 20.734. And again, I can test it if I want to by using the Pythagorean theorem. According to this, since A is 17 and B is 11.904, 17 squared plus 11.904 squared should equal 20.734 squared. I can test that quickly on the calculator. 17 squared plus 11.904 squared equals 430.705216. Take the square root on both sides, and I get 20.753. So again, I'm off by 1/1000th because of my rounding. 1/1000th when you're comparing something with a length of 20. It's not a huge deal unless you're making spaceships or something that really needs really tight values for engineering. Being off by 1/1000th is usually not a huge deal. Of course, if you are worried about that, round to 5 digits, round to 6 digits. And then at the end, once you've done all your calculations, round your final answer to 6 digits or to 3 digits, whatever works for you. But I think this is plenty close for what we're doing. All right, and then we've got one more question. We did like a real life application in class where we measured the distance across, I think it was the Grand Canyon. We created like a giant triangle. Maybe somebody was doing some surveying before satellite data was available and measured two miles across the short side of the triangle. They wanted to figure out this distance across the canyon, maybe from one fort to another or one office to another, maybe it's like a Bureau of Land Management or something. And we're trying to figure out the distance X. And we've got this 76-degree angle. We did some work and we found that this was equal to, I think it was roughly 8.03 miles, something like that. So similarly, let's say we're part of the National Park Service and there's an observation deck at Mount Rushmore. That's what this blurry thing is up here. And we know that if we're looking at this from the deck, it's a 24-degree angle of elevation, and it's 1,000 feet out to the base of the mountain that Mount Rushmore was carved into. So if I wanted to figure out the height from this base to the top of George Washington's head, I could do that by just solving the triangle. We've already got a lot of information. I just fill in what I don't know, but I can figure out easily. This is 74 and this is a right angle. That means that this angle up here is 66 degrees. So now I've got all 3 angles. I don't even need that third angle technically because I can just use this 24-degree angle as my theta. If theta is equal to 24 degrees, then I can figure out B. I can just say tangent of 24 degrees is going to be equal to my opposite, which is B, over my adjacent, which is 1,000. If I want to solve for B, that leaves me with 1,000 times tangent of 24 degrees is equal to B. This comes together very quickly. 24, take the tangent of it, and I'm going to multiply that by 1,000. That gives me 445.229 feet. Whoa, what was that? 445.229 feet. And rounding to 3 digits, 1,000th of a foot is very small, less than a millimeter. So I think that's probably fine for anything that we're calculating in regards to a mountain. All right. So that was kind of the rushed version of the chapter 1 or 9.1 questions. I'll have a follow-up video for 9.2 after this. As always, if you have any questions, please send me a message on Teams or send me an email. I am around throughout the day to help people out. All right, see you guys soon.